Hey folks, today's topic is differentiation rules. Those that might remember from the spring when we did our derivative shortcut, or if you've done this in physics, this is not the derivative by definition. So the derivative by definition is that difference quotient thing, the limit as h approaches 0 of f of x plus h minus f of x all over h. And so this is what we call, like I said, the derivative shortcut. I might refer to this as the derivative shortcut. You also will see this called the power rule. Anyway, okay, let's get going. So a couple of things here. This is some notation. dy dx is notation that is equivalent to f prime of x, which is the same as y prime of x. All these things mean the same thing. They're a noun. It's the derivative. So when you take, if I give you some function and I say find dy dx, that means that you go and find the derivative of it, and then that answer is dy dx. It's a noun, it's a thing. Versus ddx, this is a verb. This means to take the derivative. Ooh, how about I spell that right? Derivative. So, in other words, kind of look at the difference in notation here. Find the derivative, so we would find dy dx, where this is saying d dx of this. So this means the derivative of this thing is this thing. So it's a little bit of a, it feels like kind of a nuanced, subtle point, and I would agree that it is. But if I said find the derivative, you would find f prime. If I just put d dx around some function, that means find the derivative as well. All right, so let's start off with the easy part, the derivative of a constant. So if you think about it, right, the derivative is the slope of the tangent line. The derivative is the rate of change. So if you have a constant line looks something like y equals 6. I draw the constant line, y equals 6. What's the rate of change? What's the slope of that? The slope of that is 0. So the derivative of a constant is 0. So if you don't have a variable and you try to derive it, that piece automatically becomes 0. So let's do a couple derivatives here. What's the derivative of y equals 8? Well, just said that's the constant. This would be y prime equals 0. F of x equals 0. This is also a horizontal line. That's at a height of 0. When we take this derivative, it has no change. So now we would call this f prime of x would also equal 0. The derivative of 0 is 0. And then we finally get another function. We're doing a little different letter here, s of t. So then we would write s prime of t equals, what's the derivative of 3? 0. There is no change. No matter what you plug in for t, you will always get an answer. No matter what you plug in for t, you'll always get an answer of 3. There is no change there. Now, this is the last one is a little bit, you got to be a little bit nervous here. You got to be a little bit not nervous. You got to be on edge. You got to be alert. That is a better word, not nervous. Alert. You got to be alert. This feels like a function. It's not. It is a function, but it's a constant function. It feels like it's something like this. But what does this have that this doesn't? It doesn't have a variable. Well, you might say, well, wait, isn't k a variable? No, they told us that it was a constant. So if they didn't tell us that, then we would assume k to be a variable. What about pi? It feels kind of like pi should be a variable, but it's not. What I'm trying to say here is if you're going to make a mistake, some kids would do this. Y prime equals 2k times pi. If you don't know how I got that, we'll talk more about that as we get actually in the next example here. But what I want to point out is this is not true. It's not true because pi is a constant. If k is a constant and pi is a constant, then they're both a constant. And what's the derivative of a constant? 0. So don't fall for that. Be alert. Sometimes they'll try to throw a couple curveballs at you. All right, now we're talking about the power rule. This is the biggie. This is what I would call the derivative shortcut, the power rule. He calls it the powerful rule. And here's the idea. You have to have your function look like this. You have to have it in the format of ax to the n. Then it turns out that the derivative of this, the derivative of ax to the n is equal to an x to the negative 1. So notice what happened here. My coefficient got multiplied by my exponent, a times n, ended up being a times n, and then we subtract 1 from the exponent. That's the derivative shortcut. That's the power rule. Number 1, mult coefficient by exponent. Number 2, subtract 1 from the exponent. So there's your 2 steps. Multiply the coefficient by the exponent, and then subtract 1 from that exponent. Now, yet again, I've got to be careful here. I've got to make sure that my function is in this format. I kind of think of it as like a polynomial format. It's not a polynomial, like you'll see some of these root stuff. But I kind of think about that as kind of like what we did when we did quadratics back in Algebra 2. All right, so let's take a look. Our first derivative, our first function here is 2x to the third. We're in the good format. We've got a coefficient, we've got an x, we've got an exponent, so we can just straight up derive this. F prime of x is equal to, all right, remember, what are the 2 steps? Multiply exponent and coefficient. So 3 times 2 is 6, and then I subtract 1 from the exponent, we get 6x squared. All right, so that's the basics. Now I expect you guys to be able to do all. I'm not going to probably show an example this easy again. Now, this is the next level. All right, so we've got a couple problems here. We don't really have a coefficient. It doesn't feel like we have an exponent. We have this root around things. So we're going to do something called a rewrite. Rewrite. A rewrite, he calls it simplifying early and often. I want to try to reorganize this thing so that it looks like coefficient x to a power. So let's do a couple things first. Well, let's do this first. What's our coefficient? There actually is a coefficient here. It doesn't feel like it, but there is. This is a sneaky way to write what's in front of this is a 1. And then we get 1 over 3. This is a sneaky way to write 1/3. But that's what it really is. Then we've got to go back and remember, what do we do with what do we do with roots, and how can we rewrite them as an exponent? Well, I always remember this one. So I always go and I think, all right, what is it with square root? So I would say, all right, so the square root of x is equal to x to the what? X to the 1/2. This is something worth memorizing. So this is a square root, which means a 2 root. That becomes x to the 1 over 2. So if this is a cube root, what's my exponent going to become? To the 1/3. And then a 4th root would be to the 1/4, a 5th root, and so on. And then later on, in this example here, we'll get to the spot where what happens when you've got a root and an exponent at the same time. Hopefully you remember this. If not, we will review it. All right, so now we've done our rewrite. Do you see how this now looks like that? They look the same. The same setup, I should say. I've got a coefficient. I've got an x to a power. So then I can do now the derivative shortcut. So g prime of x equals, I start off by multiplying exponent and coefficient. Now look, if you stink with your fractions, then you go over to the margins, because you're not going to be able to use a calculator on something this easy. So you got to go over to the margin and do a little bit of work if you can't do that in your head. So let's review. So I'm going to take the 1/3 out front, and I'm going to multiply it by the exponent 1/3. Now, in this case, we have a common denominator, but you don't need a common denominator when you multiply. You can multiply just straight across. So 1 times 1 is 1. 3 times 3 is 9. So I get a new coefficient of 1 over 9. Then x to the, all right, now if you can do this in your head, great. If you can't, go to the margin and write it out. What I mean by that is I want to subtract 1 from 1/3. So I would take 1/3 and I would subtract 1. That's the second part of the derivative shortcut. I multiplied the coefficient by the exponent, and now I'm going to subtract 1 from the exponent. Now, I don't like to mess around with this. I don't like to rewrite it. I know I need a common denominator here. I'm not going to rewrite. I'm just going to put it right on top of this. I'm going to change the 1 into a 3 over 3. So now I can subtract 1. I have my common denominator of 3. And then I can now subtract my numerator. 1 minus 3 is negative 2. And then I can bring that back into my problem. Negative 2 over 3. Now, if this is a free response, you could stop here, game over, but they would probably never give us something this easy as a free response. So now we want to clean up. So to clean up, I usually like to take care of a couple different things. I'm going to take care of the negative. What does a negative exponent mean? And then I'm going to take care of the rational exponent of 2/3. What does 2/3 mean? Okay, so let's start with the negative exponent. Remember, that means flip. That means flip. So this, if I were to turn this thing into a fraction, it would be over 1. So when I flip it, it would end up on the bottom. But I already have a denominator, so I'm going to flip this into the bottom of this one with this 9. So I've got g prime of x equals 1 over 9 times. Now, when I flip this to the bottom, I've got to remember how these work. Remember, the 1/3 was the same as a cube root. So I know that I've got a cube root here. Now, I always like to put this multiply symbol between my coefficients and my roots so that I don't get those two things confused. Now, how do I write this 2? What role does that 2 play? That ends up being my power. So x to the 2/3 can be rewritten as the cube root of x squared. Okay, let's have you try to do this one. Take a pause here and give it a whirl. All right, let's see how you did. The first thing I noticed is that I need a rewrite. This does not look like that. So I do have a coefficient, so that part's nice. I've got 5 over 3. And then x to the, okay, what's the price for taking this x to the pi off the bottom? The price is that I would have to move it to the top and change it to a negative. So there's my rewrite. Now that I have it in this format, I can follow the derivative shortcut, which says y prime equals, which says take the coefficient and multiply it by the exponent. So 5 over 3 times negative pi would be negative 5 pi over 3. X to the, and then the second part is I would subtract 1 from this exponent. Now on these other ones, when I subtract 1, I get a nice number. In this case, I wouldn't get a nice number, so I'm just going to leave this as negative pi subtract 1. There really isn't much that I could do to make this look nicer. I could bump this to the bottom and get rid of both those negatives, but it still would be pi plus 1. It wouldn't be very nice. All right, you're up again. I encourage you to pause here and try to do part D on your own. All right, let's see how you did. First of all, hopefully your math voice is catching on to this. I need to do a rewrite anytime it's not in this ax to the n format. So my coefficient is 6 over 1, so that's just 6. X to the, okay, we got a lot going on here. This x is on the bottom, so when I bump it up, it's going to need a negative exponent. And then also, I've got a 5th root and a 3rd power. You've got to keep this straight. That's why I memorize this, because I know this is a 2 here, and that's a 1 there. That's how I remember this. So it's up to you how you remember it. I mean, that's your call. But you've got to remember, you've got to keep those two things straight. So this is going to be the 3rd power with the 5th root. So now we've done our rewrite. Now if you couldn't do the rewrite on your own, all right, well, you're learning. So pause it again and try to finish this on your own. All right, let's see how you did. So now I'm going to do y prime equals coefficient times exponent. So that would be negative 18 over 5. And if you can't do that in your head, go over here into the margin and do that multiplying again. And then I would get x to the, and now I need to subtract 1 from this. So if I lose from negative 5/3 minus another 1 would be negative 5 more, so that would be negative 8/5. Now, I'm probably going to give these mostly as free response problems, but you'll never see that on the AP test. So you always will have to clean up. So my cleanup, I've got a couple of issues. I've got the negative, that means bump to the bottom, and then I've got 8/5, which means I need to turn it back into its root format. So y prime would be equal to negative 18s on the top by himself. Then I've got the 5, and I like to put the multiplier symbol so that I know that these things are separate. Okay, the 8's on the top and the 5's on the bottom. That means the 5 is the root, so this is the 5th root of x to the 8th. Now here, you'd never see an answer like this in a multiple choice section because you can clean this up even more. Look at this and think for a second, how could we clean that up? All right, let's see what your math voice said. See if it said the right thing. In this case, if you think about it, this is a 5th root, and what kind of things escape 5th roots? 5th powers. Well, I have an x to the 8th here. That means I have at least 5 x's. So what I'm going to do is I'm going to take this and I'm going to separate it into x to the 5th times x to the 3rd, all underneath a 5th root. Remember, we did this with numbers before where we'd break up, like let's say the number 20, we'd break it up into the number 4 times 5 because 4 was a perfect square, which was allowed to escape a square root. Did I say 20? I meant square root of 20. We're doing the same thing here, except to be able to escape a 5th root, you need to be a 5th power. So once this escapes, what does it look like? So I would have y prime equals, I still have my negative 18 on the top, over, all right, now I still have the 5 on the bottom, but this x to the 5th is going to get 5th rooted, which just leaves us with x. And like I said, I always like to put a multiplier separator between my terms and my roots, especially when they're weird roots like 5th root. So I still have a 5th root, and that x cubed is still trapped inside. Now, if you want to be really picky, you might say something like, well, wait, we still have a root on the bottom. Isn't that bad news? In this case, it's more of a hassle to clean it up than to make it, and it doesn't get much nicer. So you'd have to times by 5 of these, right? Because you want a 5th root. When it was a square root, we just have the times by square root over square root. Well, I'd need 5 of them to cancel out a 5th root. So it actually, we kind of turn away from it at this point and kind of say, yeah, we're good. If f of x equals blah, 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 find each of the following. F prime of negative 1, f prime of 0, the x coordinate where f has a slope of 128. All right, so in either case, we're going to have to figure out what f prime is. So as I look at this, do I need to do a rewrite? Maybe. If you see that as a rewrite, eventually we're going to get to a spot where this just is naturally in our head. I'll do a quick rewrite over here. So I'll do it up here. Normally, I wouldn't do a rewrite here, but since this is the first time we're seeing some of this stuff, we'll practice it. F of x equals, all right, so I have my x to the 4th. I like that. This 2 is messing me up, but that's just a coefficient. So if I take the coefficient in front of the x, which is a 1, and I put it over the 2, I have an overall coefficient of 1/2. So now that I've done my rewrite, I can go ahead and calculate my derivative. Therefore, f prime of x is equal to 4 over 2, which is 2, and then subtract 1, which is 3. Now I'm going to use this to help me answer some of these questions. All right, so if I wanted to figure out f prime of negative 1, guess what I would do? I'd plug in negative 1 in for x. All right, a negative 1 3 times would still be a negative, times 2 ends up being f prime of negative 1, ends up being negative 2. F prime of 0 equals 2 times 0 cubed. 0 cubed is 0 times 2 is 0, so f prime of 0 equals 0. Now find the x coordinate. Okay, so we're trying to find the x coordinate. We're trying to find the x value where f of x has a slope of 128. All right, slope of 128. You guys have to get to the spot where you can start to interpret this. This is saying the slope equals 128. Therefore, what does that mean about f? That means f prime of x has to be equal to 128. These are the connections you guys got to start making, and this is the basic stuff right now. Now, this is the first time you're seeing it, so I get it. Maybe you're not making that connection yet, but you've got to start making that connection. So slope of 128 told me that m was equal to 128, which means the derivative must be equal to 128 because slope and derivative are the same thing. So let's go ahead and calculate this now. So I first have to take f prime of x, which is 2x cubed, has to equal 128, which is the slope. So now I can start to set up, I've got the equation, now I can start to solve it. So what would you do to both sides? I would divide by 2, x cubed equals 64. Who's keeping x from being by himself is cubed, so I'd have to cube root. And yes, this would be something they would expect you to be able to do in your head. What number cubed ends up being 64? Well, let's start with 2. Well, 2 times 2 times 2, 8. Then move on to 3. 3 times 3 times 3, 27. 4 times 4 times 4, probably, maybe. Let's do 5 times 5. No, wait, this can't be 5 times 5 times 5 because that would end in a 5. So I know that that's not it. And plus 5 cubed is 125. Yeah, so this is 4. So what is the x coordinate when f has a slope of 128? That's when x equals 4. Now, let's say they wanted you to figure out the function value. Instead of saying the x coordinate, what if they said point? Okay, so if they said find the point, then we'd have to plug in 4 for x into my function, not my derivative, into my function. So 4 to the 4th, that's what we just figured out. That was 64 times 4, which is 256. Well, let's do this. Let's take 64, cut it in half, which is 32, and then times that by 4, which is 128, I think. So if they said find the point, you'd have to plug it back in. But remember, this is x. This is x. This is f of x. That's x, and then that's f of x, not f prime of x. If they said find the point of f, you'd have to plug it into f. All right, so if example, so we've got this function. Find the equation of the tangent line at x equals 2. Boom. You should be getting good at this now. You got to leave yourself a little note. Find the equation of the tangent line. You want the equation of the tangent line. What do you need to know? You need to know the point, and you need to know the slope. What can you tell me about the point? Well, hopefully you can tell me that the x value is at -2. How did you find the y value? Take it and plug it in. Plug it into your function. So this is x, this is f of x. So I'd plug it in, that's 4 times 2 is 12. What do we know about the slope? The slope of the tangent line is the same as the derivative at that location. So I'm going to take the derivative at -2. Well, let's go up here and see if we can figure out what the derivative is first. That's pretty easy to find the derivative. Therefore, f prime of x is equal to 6x. So now we would plug in chug. Plug -2 in that, we'd get a slope of -12. And now I just said write the equation, so you could write it in any form that you want. If you wanted to do point slope, go for it. If you wanted to go solve for the y-intercept, go for it. I'm going to go for my favorite form, which is Taylor. So we would say y equals y slope x minus x to turn into a plus. Find the equation of the normal line. Okay, we got to start to get good at this. Equation. Let's highlight again. Equation of the normal line. First of all, if you're going to find the equation, what two things do you need? You need the point, and you need the slope. All right, so that's anytime I see the equation for a line, I need those two things minimum. Now, this is for the normal line. So the point isn't an issue. The normal line, remember what the normal line is. The normal line is the line that goes through the curve perpendicular to the tangent line. So if I were to sketch this, how do I want to draw my curve? It's always tough to make sure you draw one that's easy to find the tangent to. Okay, this is F. We have one line that's called the tangent line. Let's say that we want to figure out, and this is C. That's the value that we're trying to figure out the tangent line at. So through this point then is C comma F of C. That's the point that you know the X, so you plug it in to get the Y. Now we've got this thing called a tangent line. The tangent line has the same point, C F of C, and its slope is the derivative. The way that line is curved, the slope of this line is exactly the same rate at which the function f is changing at that value. We have this other line called the normal line. Now the normal line is perpendicular to the tangent line. This is what we call the normal. Now what's interesting is the normal has the same point, C F of C. It goes through the same point, but its slope is equal to the perpendicular of f prime. Its slope, these two meet at a perfectly 90-degree angle, therefore they're perpendicular, and so the slope of this is equal to the perpendicular of the slope of this. So what does that mean for us? Well, as we come down here now, we can start to plug and chug a couple things. Our point is still -2, 12. The normal line, the function, the tangent line all share the same point. The slope, though, is the perpendicular of the derivative at -2. So in this situation, the slope at -2 is -12. The perpendicular to that, opposite and reciprocal, would be -1 over 12. Try again, stuck. How about +1 over 12? Sorry. +1 over 12. Opposite, that's negative. I need to make it a positive. All right, now we can take these two things together and we can make an equation for the slope of the tangent line. Sorry, we can make an equation for the normal line. Y equals my y value plus my slope over x minus my x value. Okay, now those are a biggie. The next one, I don't know. And the next one, I don't know if you'll see that one as much. But this idea of what a tangent line is and what a normal line is, those are big deals. Those are biggies. So we're supposed to find the points where the normal line intersects the graph of f. So we're supposed to see where does this hit there. Well, one of them should be easy. One of them should be at negative 212. We should know that. That one because the line, let me try again. The curve, the tangent line, and the normal line all share a point. Now what's interesting, now this function here that I made, let's say it goes down like this. This line, normal line, maybe intersects the curve in more than one spot. Oh, why didn't I draw this curve as what it actually is? Good night. That was silly. I could have drawn like, that's quadratic family. I could have easily drawn, whatever. Okay. So we want to figure out where does the normal line intersect the graph? Well, how do you figure out, what kind of algebraic equation can you make when you want to figure out where this thing hits this thing? Well, we just set them equal to each other, right? I could just take one and set it equal to the other. So I would take 3x squared. I want to figure out when my function intersects or shares the x values, where they have the same x values. Now I can start to clean this up. My math voice says to distribute that 1/12. That'd be 2 over 12, which is 1 over 6. My math voice says clear out those fractions. So I want to find something that I could multiply by that would cancel a divide by 6 and a divide by 12 at the same time. So I'm going to use a 12. Now the trick here is you got to make sure that you multiply everything by 12. So this would become 36x squared. 12 times 12 is 144. 12 times 1 over 12 is 1, so that just leaves x. 12 divided by 6 is 2. Now I can take this thing and I can start to clean it up. Oh boy. So I would have 36x squared, subtract x. So that's 146, but I'm going to move it to the other side. So that's negative 146 equals 0. Good night. We're supposed to factor this without a calculator, which is going to be next to impossible. But what's nice, wait a minute now. Wait, let's think about this for a minute. What do we know? What point do we know? What do we know is one of the solutions to this? When you factor this, what do we already know? We know it has to be, I know that one of my factors has to be x plus 2. How do I know that? I know that because the point negative 212 is shared by these two curves, by the f curve and the y and the normal line. So I know that x plus 2 has to go into this. So what I can do now is use synthetic division to figure out what this is. Sneaky, right? How would you ever think to do that on your own? I agree. I don't really expect you to have seen that on your own, but now you're seeing us together do it. Maybe you'll remember it next time. Okay, so I've got a negative 2, I've got a 36, negative 1, and negative 146. So that's 36, that's negative 72, that's negative 73, that's 146, and that's 0. So that means that my two factors are x plus 2 and then 36x subtract 73. Now we're supposed to figure out the two function values, or sorry. We're trying to figure out the 2 points. Well, one of the points is real easy. We've already figured out that this one is at negative 2 and 12. So once I ZPP'd that, I took the negative 2, I plugged it in for x, and we figured out what the y value was. This one's not so easy to figure out, but remember, this is a free response. So I'm not going to do a whole heck of a lot here. If ZPP this, you got to do this part on your own. So that would be 73 over 36. But then if I want to figure out what the y value is, I would have to plug that into this, which means I'm just going to plug it in there and leave it alone. 3 times 73 over 36 squared. Ultimate laziness there. I don't know what that is. How could you possibly do that in your head? But it's free response, so we could stop. So wherever this point is the other place where the normal line intersects the parabola 3x squared. Rewriting is very important. We already kind of talked about all this. Rewriting is very important when using the power rule. So rewrite as much as you can. So ax to the n, where n must be a real number. All right, so let's have you try to mess around with some of this. You could probably, actually, you should be able to do all of these on your own. All right, if you haven't paused yet, I really encourage you to pause and at least do one at a time. All right, start with our rewrite. Rewrite. My coefficient is 5 over 2. This is on the bottom, so I'm going to bump it to the top, which costs me a negative square root of 2. Now look, I don't like that exponent of root 2, but it's fine. It's an exponent. It's legit. It's a number. All right, the derivative shortcut comes in two forms. You take or two steps, I should say. Multiply. Now, because they said take the derivative of this, you don't have to write like y prime or anything. You are just then, whatever you write is the derivative of this. Dang it, no, I got lazy. What I should do is still have this around there. d dx. Sorry about that. This should still say d dx of blah, because that doesn't equal that until we take the derivative. Now we don't have to write the d dx anymore. We can just start taking the derivative. So 5 over 2 times negative root 2 would be negative 5 root 2 over 2. X to the. Now, because of this, I need to subtract 1. But when I subtract 1 from this, there's not going to be anything to really clean up. So this would be where I would leave it. Now, this is a free response, so you could stop here. If you wanted to do a little bit more cleanup, we would then have this. I would take out the negative and bump it to the bottom. So I would have negative 5 square root 2 over 2x to the square root 2 plus 1. That's what it might look like as a multiple choice. If this were a free response, definitely stop here. Okay, like I said, I'm encouraging you to pause, please, pause, and then try it on your own. All right, let's see how you did. So I'm first going to do a rewrite. Now my rewrite, I'm going to take this into account. So I'm going to take in 2x to the third. That means the 2 is getting cubed and the x is getting cubed. So this is going to be equal to, I'm still taking the derivative of. So now I've got 4 over 2 to the cubed is 8. X to the cubed is x third. X to the third. That was just a rewrite. I'm going to rewrite again because I've got an x on the bottom, so I'm going to bump that up. So that still equals d dx of, I'm still deriving. I'm going to clean up the 4 over 8 at the same time here. So 4 over 8 is 1/2. X from the bottom to the top costs me a negative exponent. Now I can derive this thing, and I don't have to write d dx anymore. So that would be negative 3 over 2. Subtract 1 from the exponent would be negative 4. And then a cleanup. This is pretty easy to clean up. I would have a negative 3 over 2x to the fourth. Again, I encourage you to try to do this on your own. Pause and go. All right, so we're going to do a rewrite here. So that's going to be equal to d dx of, I'm just going to take care of the root on the bottom first. So that's going to be 7t over 3t to the 1/2. Which I can then rewrite again. I've got to take this t from the bottom and bump it to the top. Now there's already a t up here. So when I bump this to the top, I'd have t to the first, and then I have a t to the negative 1/2. So 1 take away 1/2 is 1/2. So this ends up being my coefficient of 7/3. T to the 1 take away 1/2 is negative 1/2. And now I have it in my format, ax to the n, which means I can then derive it. So I don't need the d dx anymore, so I'm going to take 7/3 times negative 1/2 would be negative 7/6. T to the subtract 1 would be negative 3/2. Dang it. This is supposed to be a positive 1/2. Because it's 1 take away 1/2. Sorry about that. So this then would be not negative 1/3, but negative 1. Sorry, not negative 3/2, but negative 1/2. Now this has two things that I'm going to fix. This has a negative exponent, which means bump to the bottom. And then it has a fractional exponent, which means roots. So my best cleaned up answer would be negative 7/6 times, I like to put that times in there, square root of x. Dang it! T. Rats. Yeah, I kind of saved it. Kind of looks like a T, huh? All right, last one's on you. Look at Corpy changing the letters on us. Ugh. All right, you try the next one. So we're going to start off with our rewrite. What two colors haven't I used yet? Let's try these two. Okay, so my rewrite equals d dx of, doing a rewrite here. I'm going to take care of the quantity first, so I'm going to kind of like quote-unquote distribute the negative 2. So I would have 6 over 3 to the negative 2, m to the negative 2. There's lots of ways to get there, so if you want a different route here, just be patient and see if we end up at the same place, which equals d dx of, okay, now these negative exponents means flip to the top. So that would be 6 times 3 squared times m squared, which I'm still rewriting. I'm not ready to derive yet. So 6 times 3 squared is 9. 6 times 9 is 54. M to the second. How nice. How nice. That cleaned up so pretty. All right, derive that thing. 54 times 2, you should be able to do this in your head, or at least draw the multiplication. 108 m. Yeah, I think we'll stop here then. We'll stop here. Next set of notes coming next time. So get after some of that homework. You can at least do, I know, the first page and then a little bit more off the top of my head.